Right, our next speaker who's setting up, almost there, is Julien Vanegue, and towards Temporal Adversarial Logic.
Okay, where can I put it? Just, okay. Be careful for it to be on. Like if you don't see it green, then yeah. And sorry. A little more. I'm sorry. Okay. Can I put it here?
Yeah, anywhere you want.
You know what? You just try to put it yourself, because I'm not doing it right. Yeah, that should be fine. Okay. Can I put it yourself?
Test.
Yeah, just put it this side. Try now.
Okay. Good.
Just trying to move it. Okay.
Yeah, let it go. Hello, can you hear me? Yeah. Good. Hello, my name is Julien Vanegue. I'm with Bloomberg and Imperial College London, and we'll talk about a work in progress that is about trying to bring the temporal reasoning to under-approximate logic. So why would we want to do that? First of all, temporal logic has been massively popular in the last 40 years for model checking and other techniques to verify programs. And so we're not going to reinvent anything of that. However, there's a reason why we may want to do more with temporal logic is because in the last few years, timing bugs and timing attacks have been on the rise. And not only in cryptographic code, but also in general purpose code. For example, if you start mixing untrusted data and trusted data in a browser, for example, you may be able to infer properties of the trusted data based on your untrusted data, say they contain the same containers. So there are a number of code patterns and classes of vulnerabilities that have been on the rise. And it's legitimately why we're asking ourselves whether we could actually use some of the temporal reasoning within the incorrectness framework. So that's why we're doing that. A little more concretely, many of you will be probably familiar with the model logics. So of course you have LTL, linear temporal logic, CTL, TLA, folks like Manap, Nueli, Lampert, and many people after them who actually worked on those logics for quite a while. However, if I put my developer's hat for a second, it's a little bit hard for me to really use those tools. Usually you need a verification engineer to go with you and actually annotate your code or do things on the side that is not intuitive for people who actually may benefit from those tools. And so one of the motivation of this work is really to be able to create a program logic, something that maps to the semantic of the programming language in your programs, and encode the timing information within the rules, within the triples, if you will. And so you may have assignments and then conditionals and while loops and so on. And even more particularly, we want to be able to do this in the under-approximate setting. So adopting incorrectness logic. For those of you who were in a talk at Orhans you've seen that already. But basically, adversarial logic is a mixture, a marriage, one could say, of incorrectness logic and the Dole-Fiao model, where you have an active attacker represented in the logic itself. So typically, you're talking about a parallel composition, P and A, where P is a program, and the target program, and A, the active adversary trying to sabotage you, trying to exploit your vulnerabilities. And it's not only for cryptographic protocols, it's also for regular code that in fact is vulnerable to some bug that could be at deeper level of interactions where you need multiple interactions with the target program to actually reach a vulnerable state. And in particular for the timing work, we care about relational properties. For those of you who may have noticed, in this relational adversarial logic paper, which is still being reviewed. In fact, I changed the perspective of adversarial logic from a saboteur model, which I call, to an arbiter model, where in fact your adversarial program here acts, instead of trying to actively sabotage you, is trying to actually execute several executions of your program or several different programs and prove them not equivalent typically, or try to prove that certain execution of your programs are leaking some information, which is what we're going to talk about here. And to illustrate our purpose here, we're going to take this example, which is quite artificial, but really actually is sufficient to really understand what we're talking about. On the left-hand side, you have a program, a target program that contains an information disclosure bug. And on the right-hand side, you have an adversarial program trying to actually exploit this particular vulnerability. So let's look at the left column for a second. You have a couple of different random values stored in global variables sec1 and sec2. Say for secret 1, half of secret 1, first half of secret 1, first half of secret, the second half of secret. And then you have a while loop that reads a couple of values in variable x and y, and then it tries to see if the value of x that you just read from the channel S is actually different from the first part of the secret. If so, it returns a value, a status code, say 0. And then after that, it's going to try to check if the second part of the secret is equal to your second value read on the channel, say y. If y is different than the secret, the second half of the secret, then it's going to log a failure, and then return the same error code 0. Otherwise, it just returns error code 1, or status code 1. And on the right-hand side, what you try to do is to satisfy an adversarial contract, an adversarial assertion, where you want this particular assertion on line 7, you want the return, the value that you read back is actually 1, meaning that you executed line 14 on the left-hand side. And so we have those symbolic variables, alpha 1 and alpha 2, and really the goal of the logic is to solve for those variables. What variable do I have to actually put in those values to exhibit the fact that, in fact, I can reduce the complexity of the attack. Here is in fact, 64 bits attack reduced to 2 times 32 bits. So it's way faster to actually attack the first part of the secret first and the second part of the secret later, knowing that you can differentiate between the 2 kinds of error at line 9 and line 12, because there is this log call, and that log call is very time consuming. Right? That's the intuition. And so what we're going to do at the logical level to encode this is we start from the incorrectness triple, where you have, for all states in Q, there's a state in P that is in the relation C, with a little epsilon can be either OK or error for the correct computations or the error computations. So we call epsilon a little tag. And in the adversarial triple, in adversarial logic, this tag is actually on the left-hand side as well as on the right-hand side. And the reason for this is because in adversarial logic, you can transitively reason about the knowledge of your adversary. On top of that, we add what you could think of as a little ghost state theory for tracking time. And what you do, in fact, is you parameterize a triple with a little time footprint, which is this big delta, and this big delta is dependent not only on the precondition P, the preset that you were executing your program in, but also the specific piece of code that you're executing, say C. And when it's actually ambiguous, we're just removing the C, we just write delta P. And similarly, the little epsilon is still OK, and or add, which is a generalization of this error tag for the adversarial computation. And so we're tracking, we're mapping that T1 to T2 by adding this footprint. Okay? And so how do you use this in practice? For example, if you want to exchange messages, you're reading or you're writing messages, you can use the Flory's axiom of assignment generalized to lists, where if you're reading a value in variable x from channel S, right, you're starting with a precondition P, and x is whatever value you want, and S, the channel, actually contains a list of value L. Well, in the post condition, what you're going to have is that you're going to update the channel represented as a list, where you're going to append this triple, this epsilon T2, and x and in being like an input information that you're putting into your channel to track that this particular event was an input event. And you will map T2 equal T1 plus your little time footprint. When you're writing, it's quite similar. However, the triple that you append to your list is using out, meaning that it's tying it as an output event. And as you see, it's monotonic, meaning that you don't have any interleaving semantic needed here, because you're just like appending data to both channels, and at the end you synchronize the reads and the writes event. And so, and on top of that, really important is that as part of those values that you push or that you put at the end of your list, you have the time footprint. So this particular value, the value of T is actually also put together on the channel. So T2 in that particular case. Okay, and similarly, you can very easily write summaries in your in this logic, where instead of actually going down a rabbit hole of analyzing the log function, you can just say, you know what, if I start my program at time Tn, and then I execute log n, well, I can, for example, say that this is going to take 100 cycles. And so it's very easy. It's almost cheating, one would say, but it's just to show that it's a very practical way of thinking about how to analyze timing. Okay, and so I mentioned about the reads, about the writes, but how do you actually match that up after that? Let's look at this graphically. So the rule is a little bit complicated, and it's probably not in its final stage at this point. However, graphically, it's pretty clear what happens here. On the left-hand side, the two left columns, you have the process or the program that reads something into variable y. And on the second to left column, you have this write event, right, that writes the value of x. And the result of that, evaluating that, will actually produce two new executions. One where the y is replaced by the value that was in x, and then there is a residue, let's call it a execution for the right-hand side of the program that actually performed the write. But really, what's important to see here is that when you are, there is a the timeline of those events is actually being synchronized on the right time. Meaning that if you have a program, you're trying to attack a program that is doing a read, well, you can actually synchronize on the attacker timeline based on when you're going to write the value. And that's exactly why when you have those messages that first you send something, it gets read, and then something else is written back, and you read that, you can an adversary can actually synchronize the target program on its own timeline. That's really important here. So here you started with a process that went from P1 to Q1 on time T to T prime, but then when you actually compose this in parallel to a process that writes, then you will actually acquire the timeline u prime of that process. You will not preserve the time that you executed with. And just similarly, when you take two executions, right, one is reading and writing, the other writing and reading, what happens is that those are not equivalent to, you can actually extract those, the differences of those time footprints. So I've had a number of discussions with people since I'm here about, oh, it's so complex to do relational analysis in the verification setting. You know, you have alternating predicate complexity, for all there exists, for all there exists, etc. It is very hard in the verification setting. However, we're not doing verification here. We're extracting behavior. So that's much easier. All right, and on top of that, I was interested in finding out whether there is some kind of structure to these timing interactions. And so I started to draw those boxes where you have a bunch of states, right, at, say, 3 different states at time footprint T1, say, and then you have a number of execution paths that go through. And those execution paths, actually, you see that you can go from the set of state at time T1 from the set of state at time T2 by actually using this time relation, let's call it now, epsilon 1. And similarly, you can go from those states at time T2 to time T3 with this epsilon 2, meaning that if you start composing those epsilons, in fact, you can go from time T1 to time T3, etc., etc. So where I'm going at with this is that it seems like there is some nicely formed algebraic structure to this, in the sense that you can exhibit the the special elements of that algebra. You have the, say you have an identity, you have a zero element, you have what we would say the common elements, E of the other Unitarian element, where you go from t to t plus 1, and then you can actually iterate over that. You can go from t to t plus v times n if you have a number of repetition in a loop, for example. So it appears like there is more research necessary to really ensure that, but it appears like it's possible to actually map that to an algebra. And to conclude, there's a lot more work to get done to actually get from a, let's say, a temporal logic for verification to a temporal program logic where you track those time footprint, and particularly in the relational case where you can attack things like constant time programming bugs, where if you're able to actually characterize those execution based on their time footprint and their timelines, based on some specific message passing, I guess, semantic, you could extract some of those under-approximation that hopefully we'll be able to find real bugs down the road. Before we get to an implementation, however, we need to think of it in terms of like instruction level semantic. There has been a lot of work, not a lot, but a little bit. I know like Hernan Ponce de Leon, for example, a couple of years ago came up with a logic to analyze side channel attacks at Oakland. However, here we under-approximate. And if we're able to actually implement this at an instruction level, I think we'll be in a good spot to be able to start finding bugs, timing bugs. Thank you very much.
Patrick.
It's just a funny remark. The trick in temporal logic by Neuilly and Clark and so on is to forget about time. In the formula, you speak of the time without ever mentioning the time, and then in your logic you only speak on the time. So there is some incompatibility here.
That's right.
Could you do it without the time? That is just replacing time by their formula or sequence of events or things like that.
I think you could probably map it to dynamic logic of RL using RL's modalities possibly. But however, one of the goals here was really to be able to map to the semantic of the programming language instead of staying at in this abstract model level of descriptions. And so in a very utilitarian, practical interest, if you will. So point taken, thank you for telling me that. And I think there's definitely way more work to actually do to get to a spot where we're happy with it.
Thanks for the talk. So one comment going on what Patrick said, there is actually time temporal logic that you may be interested in, but they are more complicated. Also in the same line, you take as an example constant time, but constant time is precisely not about timing actually, it's more about dependence from the secret usually. So probably it's a bit a complicated way to make constant time. Maybe you should look at things like constant resource, which are more about timing itself than...
Right, so here I mentioned constant time, but really what the bug is you branching on a secret value, right? If you start branching on a secret value, that's when those potential breaks of constant time programming actually happen, or the leaks can happen. So I think you're referring also to like RT, CTL, or RT, LTL, things like that, right?
No, actually, well, we can take it
sure.
offline if you...
Thank you.
Thank you for the talk. So I think I missed the basic intuition about this footprint time, so this delta thing, right? Mm-hmm. Is it, tell me if I'm correct or not, so I have the feeling it's a function that takes a command and a precondition and gives me a number. But how can, so if I set P to true, I have the feeling that it means I need to know for any state in which it started, basically how long it's going to take, which might mean it's constant time. Or said differently, I don't understand, for example, how your if rule could look like. Does that make sense?
The way I think about it is that the rules themselves, in fact, they are independent of that delta map, right? So say you were trying to map the time it takes for instructions to execute or statements to execute based on your pre-state, and that particular instruction itself. Of course, in the real life, you need to model things like caching, and etc.
Maybe so here P is a precondition, right?
Right.
So if a really simple example would be C is if X equals 0, log something, else skip, right? And my P is true. What would be the timing of that? Because in one branch, depending on the value of X, I would say it takes 100 cycles. In the other one, maybe 1. So you mean here I just choose which branch I take and then I... Or, but if it's a... Maybe I should pass better.
Well, no, I mean, just following up on that, is it a partial function? So it's like it may only sometimes be defined?
The delta?
Because if P isn't specific enough, then maybe delta is just not defined.
Right. So the way I think about it is that, in fact, the rules are parametric to that delta, meaning that they're not depending on it. And so if you provide a delta on a side, which I have, right, either you actually can provide a static delta, which I don't recommend, or you can actually infer that delta based on, for example, a runtime execution, right? So based on a real concrete execution, you can say, oh, this is a delta we're talking about, and then you don't think about it. You just...
So one last question, and can our next speaker begin to set up, please? I can't see where you are.
Thank you. I have a question about the bug finding part. So I have read your paper about adversarial execution, and my question is, you need to have the adversarial program, right?
Mm-hmm.
And so I have maybe a little trouble in understanding, but if I want to find a bug and I have to have the program, maybe this thing, I mean, it's useful to actually check that the program that I have already written, the adversarial program, that is.
100%. So thank you for saying that. In fact, if you were at Ohrenfest, you would have actually seen the work we're doing with program synthesis to be able to do this without having to provide the adversarial program. So we basically starting from this vulnerable program, and then in our talk using by abduction and program synthesis, we able to basically come to a point where we're generating the adversarial program.
Then I'll have to look into that then. Thank you very much.
Thank you very much.